All right, hello everyone, and welcome to lesson 1.2, Algebraic manipulation of limits. The way that most of these asynchronous classes will go is that I'll be using them as times to introduce to you a totally new topic, basically like a separate class. I'll be walking through the student packet, adding some details to it, so you might want to write down what I say verbally, but then asking you to pause the video and work at certain times or answer certain prompts that will pop up on the Nearpod video, okay? So as we work through, you should have your student packet out, ready to go, taking notes on exactly what I do, just like you would in class. At the very end of the Nearpod, you'll also have a chance to submit any questions that you might still have regarding any of the work that we're doing in here, because most days we actually just have to kind of push forward. Lesson 1.1 was this morning, lesson 1.2 is this afternoon for asynchronous, and then we'll be back to lesson 1.3 for our next synchronous class, so it moves kind of fast. All right, so go ahead and get started. Try this dude out here. Answer these three questions based off of the function that's given here and the table below. Go ahead and pause the video now, give those three things a shot, and then play it again when you are finished. All right, so let's go ahead and do that. We want to calculate f of 4. We're given our f function up here, so f of 4 is not too bad to do. We just got to substitute in 4, so f of 4 is 4 over 6. Which will give us, we can leave it as 4/6 in this class. I do not actually ask that you simplify anything. It's one of the magic things about actually the AP Calculus exam is you do not have to simplify anything, but why not? We can call it 2/3. All right, so there is f of 4, right? Well, okay, what is f of -1? Similar kind of process. F of -1 is going to be substituting in -1. That'll be -1 over -1 plus 2 is 1. So f of -1 is -1. All right. Not too bad there, right? All right, here's your calculus work here. What is the limit as x approaches -2 of f of x? So here's the problem, right? If we try to substitute in -2, we get -2 over 0, which is undefined. But remember, the limit doesn't matter what happens at the point. We just want to know what happens as we approach the point. So let's take a look at our table up here. As we approach the point, I've kind of done the work for you. I've approached -2 from the left and approached -2 from the right. Let's take a look. Looks like f of x as x approaches -2 from the left. We can write that down. The limit as x approaches -2 from the left. We always want to use proper calculus notation here. Otherwise, no good for us. The limit as x approaches -2 from the left is approaching 201, right? Approaches, oh, actually, let's not even say that. It looks like, if we back up for a second, right here it's 201, but the trend is that it keeps increasing and increasing and increasing, right? So from the left, our limit approaches positive infinity. Let's take a look at from the right as we come closer and closer to -2 from the right-hand side. It looks like our output values, our y values, our limit approaches negative infinity. So the limit as x approaches -2 from the right of f of x. Our values get more and more negative as we approach -2, x value of -2. So we can say that this limit approaches negative infinity. And so we can say because the limit, and we need to make sure we write these things out very properly, limit as x approaches -2 from the left of f of x does not equal the limit as x approaches -2 from the right of f of x. Therefore, I can use my little 3 dot therefore symbol. That means therefore. Therefore, the limit as x approaches 2 of f of x does not exist, all right? And that's how we would say that. Cool. There we go. A little warm up from stuff from the previous days. We really want to hammer in on that notation, though. Let's take a look at another little thing. I want you to take a look at this graph here I provided. And I want you to go ahead and answer A through H based off of the graph. And then there will be a little element that you'll need to answer on the Nearpod video, a quick little check-in about that. So go ahead and pause the video, work through those problems, and then you'll see a little question pop up on Nearpod afterwards. All right. So let's do a quick review of this one. We want to know what's going to happen to h of x up here as x approaches -1. -1 is over here, so I like to do, if it helps, like a little line. From the left-hand side, so we approach that value from the left. Looks like it's approaching +1. All right, what happens as x approaches -1 overall, though? Well, the left-hand limit approaches 1. The right-hand limit I guess we should do that one over here. The right-hand limit as x approaches -1 from the right. The limit approaches -2. Remember, we don't care what happens at the point. We just want to know where's our line going towards, where's our graph going towards, what y value, and it's going towards -2. So overall, because the left-hand limit and the right-hand limit are not equal, we can go ahead and put in here that the limit does not exist at as x approaches -1. The left-hand side and the right-hand side are not going to be equal. So the limit does not exist. What about h of -1? Well, at -1, what is the point? That is what this is asking. What is the value of h at -1? Well, at -1, the value of the function, there's our point, right? Not down there, there's a hole. There's our point. It is at 1. All right. Let's take a look at 3 from the left. The limit as x approaches 3 from the left. Well, from the left, we approach a y value of, looks like 2. And how about from the right? Well, from the right, h of x approaches a y value of 3. I'll pop that up there. H of x approaches y value of 3 as x approaches 3. That x value right there from the right. So we go to y equals 3. Again, we don't care that there's not a point there. Now we ask this question. What about the overall limit? Well, I made a mistake here. Why did I do that? The limit from the left is not 3. Come on, Markwalter. The limit from the left is 2. Learn to count there. Boop, right there. That's okay. We'll actually make all kinds of mistakes throughout the year. That's one of the things that's kind of tricky about calculus. There's so many little things you can accidentally make a mistake on. They can be a little frustrating sometimes. So from the left, I apologize, is a y value of 2. Limit, and from the right, the limit approaches +3. The limit from the left and the right are not going to be equal. So overall, our limit does not exist. But h of 3, the actual y value there, is 2. Here we go. So one of the nice things about limits is that they are fundamentally a fairly easy algebraic thing to work with. If we know certain values of limits, but not what's going on with the functions, we can actually still do a lot of interesting work. All of our algebra works like it normally would, which is kind of nice. The examples I have here are sort of our relatively basic ones. We can add limits if we know certain things. Like if we know that the limit of as x approaches c of f of x plus or minus g of x, we can actually break a limit like that up into the limit of f of x plus the limit of g of x as x approaches c. And if we happen to know those limits, basically we just add those values together. That's convenient. Same thing if we have a constant. If we have the limit as x approaches c of some constant times some function, and we happen to know the limit of that function, well, that's easy. We just do that constant times what we know the limit to be, L in this case, whatever that number is. For the product, same thing. If we know that we're trying to find the limit as x approaches c of f of x times g of x, and we know the limit of f of x as x approaches c, and we know the limit of g of x as x approaches c, well, we can just multiply those two limit values if we happen to know them like we do up here, right? And quotients. Well, if we know that we're trying to find the limit as x approaches c of f of x over g of x, and we happen to know the limit as x approaches c of f of x and the same one for g of x, then we can just divide those limits. Also works basically that same way for compound functions. If we're trying to find like f of g of x and things like that too, which is kind of nice. It kind of works exactly how you would expect it to. Let's take a look at some examples. Let's say that we're given some information about some limits here. We're given the limit as x approaches -2 of f of x, which is 4, and the limit as x approaches -2 of g of x, which is -3. Well, we have a more complex limit expression here. We could break it apart and say, well, this is the same thing as the limit as x approaches -2 of f of x plus, and we're going to add together some other function. We're taking the limit of that, and there's a constant. So if I want to, I can actually even like factor out that constant from that limit statement, because as we saw above, the factor will just multiply into whatever that limit value is. And we can actually break down this initial statement into these two things. And that's not too bad, because we know this first limit is 4 plus 1/3 times this limit here. Limit as x approaches -2 of g of x is -3. It looks something like this, right? All right, and then that becomes really easy to do. 4 plus -1 or 4 minus 1, right, will give us a limit of 3. Okay. Well, I'll do one more, and then I'm going to let y'all practice here. For b here, that's not too bad. We can rewrite this limit as the limit 3 times the limit of as x approaches negative 2 of f of x. We can factor out that constant. That'd be 3 times the limit as x approaches negative 2 of f of x. We do know from above, which is 4. And so that's going to give us a value of 12. All right. So what I would like you to do at this point then, if you could please go ahead and try C, D, E, and F. Pause the video, try C, D, E, and F, and then there will be a question to answer. All right? Go ahead and do that, please. All right, so let's go ahead and get started. Let's take a look and review those practice problems there, okay? So for that first one, we got a quotient. We can break that up into 2 limits. I'm actually going to stop with the breaking up and writing out limit expressions. I'm just going to go ahead and jump to the conclusion here. We are taking a quotient of 2 functions. We're taking their limits, so we can divide the known limits, which are 4 over negative 3. All right. Over here, we got a product of 2 functions we're taking the limit of, and we can write that as simply the product of the 2 limit values. So that'd be 4 times negative 3. We'll make sure I put that right. 4 times negative 3, which will give us negative 12. All right. Over here, a little more complicated, but we can still treat it kind of like what we did above. We're trying to find some sort of compound function when we're evaluating the limit of that compound function. So we know the limit of f of x, which is 4, 2 over, we know the limit as x approaches negative 2 of g of x, which is negative 3, and we know plus 5. So we can leave it unsimplified or simplify it down to 4 over, that would be negative 6 plus 5 over negative 1, which will give us negative 4. All right. And sort of an open-ended one here, right? A limit that would result in the answer of negative 15. I want to make sure your limit notation is right. We need to write the limit as x approaches negative 2. But there's lots of ways you could have written this. If we want negative 15, it could be as easy as saying 5 times g of x, right? That would do it for us. 5 times that limit would be negative 3, so 5 times negative 3 would be negative 15. Or maybe you got a little more ambitious and did something like the limit as x approaches negative 2 of, I don't know, we could say 3 f of x, because that would take us to 12 plus 3 or something like that. There's actually an infinite number of different sort of variations on what you could do there and how you could express that. All right. Cool. So let's go ahead and take a look at some other examples. All right. Here's an example of a compound function, right? We're given some limit that we know is 2. We know that the limit here as x approaches 4, so notice that limit is different. The limit as x approaches 5 of f of x is 2. The limit as x approaches 4 of f of x is 5. Evaluate the limit as x approaches 4 of f of x. Interesting. Well, when we're dealing with compound functions like this, composite functions like this, where we have a function inside of a function, we want to start by evaluating that inside thing first, because the evaluation of the inside will then let us evaluate the outside one. So we can maybe write it out like this. The limit as x approaches 4 of f of x is going to be the same thing as the limit as x approaches 4 of f of, we're going to plug 4 in there and just see if we can evaluate that. That's kind of our easiest thing. Well, actually, we don't even need to plug it in. We know that that limit, f of x as x approaches 4 is 5. So that'd be something like that, right? Oh, wait a minute. Well, the limit as x approaches 4 of f of x was 5, so that becomes my inside part. I know what f of 5 is. The limit as x approaches 5 is going to be f of 5 there. So we're talking about a limit, so we're approaching it. We're not really caring what happens at 5. We're approaching that x value. So this works, and we can simply say 2. All right. Again, we don't actually care what f of 5 is. We're talking about things approaching. So this 5 really is talking about this limit as x approaches 4 of f of x is approaching 5. Since we're approaching 5 in here, we know the limit as x approaches 5 of f of x is 2. All right. So core idea here, as we're sort of working through things that I want us to write down, is that, so listen carefully, you can write this down, limits follow all your algebraic rules as long as you remember the limit is evaluated first. like we did up here. We're evaluating the limit first. We're not just plugging in numbers. We're evaluating limits, and we're approaching these numbers. So I'll say the core idea again. Limits follow all your algebraic rules as long as you remember the limit is evaluated first. All right. Cool. Let's keep moving. So we've kind of dealt with abstractly this idea of limits. Let's talk about actually evaluating limits algebraically from functions, all right? There's kind of three types, and I'm going to model those real quick. The first thing you always try to do when you're looking at a function you want to evaluate the limit of is let's just try plugging things in, okay? So I'm going to try plugging things in. Notice I'm not going to put an equal sign. I'm going to put a little arrow sign because we got to be really honest with our equal sign. We can only put equal if we know something's going to be equal. And I'm just going to test something here. I'm just going to plug in the point, all right? So let me plug in 3. If I plug in 3 up here, I get 3 squared minus 9. So that'd be 0, over, when I plug in 3 down here, I'll get 9 minus 18, right, plus 8. All right. So I plugged in 3. That's the limit I'm trying to evaluate. So x approaches 3. Let's just assume we can get there. 3 squared minus 9 is 0. That'd be 9 minus 18 plus 8 is going to give us 0. Now I'm putting an equal sign because these two things are going to be equal. 0 over -1. So our limit is 0. So if you can just substitute in your point and you get some value that's not infinite and exists, then great. That is the value of our limit. That means that this function is also continuous. We don't have a hole or anything there. Let's try a different situation. All right, let's see this one. We can just try plugging things in again. The limit is approaching 3. X is approaching 3, so that'd be 3 squared minus 9. That gives us 0 again, over 3 plus 3 is 6. Hey, look at that. 0 divided by 6 is 0, so the limit is 0. All right, let's try this guy. Limit as x approaches 2. So we plug in 2. 2 minus 1 is going to give us 1 over square root of 2 minus 1. So 2 minus 1 is 1. The square root of that is 1. So that's 1 plus 1, which is going to give us half. Look at that. We got a finite value. So there we go. That is our limit, and we're done. All right. We can do this string of equal sign if we know that we're going to have things that exist all the way through. The reason we sometimes want to maybe start with these little arrows is that maybe we'll get something that doesn't exist here, and you can't say that blank, that something equals something that doesn't exist. So sometimes you'll see me just start off with these little arrow guys. Kind of a little safety measure. What makes these similar? We can plug in and evaluate, I'll abbreviate that as eval, and evaluate the limit at the limit point. All right, if we can just plug in and get a finite number, we're set. That's the limit. That's all it means. We don't have any problems. The function's continuous, and the point that we get is also where that limit is going to be. Everything's going to kind of meet right at that value. All right. But as you can imagine, things probably get a little more complicated. That's not always the case. So first we try just evaluating and plugging in. Next, we take a little step farther down the road, okay? The next step is, okay, well, let's try plugging in. X approaches 3, so if x approaches 3, that'd be 3 squared plus 9. So that'd be 18 over 3 minus 3. Oh, here's a problem, right? Here's our problem. This guy here, right? It doesn't exist. You can't divide by 0, right? We can't divide by 0, so we're running into an issue here. The thing we have to talk about then is, well, can we have a limit when we can't evaluate the point? And the answer is, well, maybe. So let's think about what happens then. As x approaches 3, you might recognize from your pre-calculus algebra classes that this means we have a vertical asymptote, right? We are trying to divide some rational function by 0. We have a vertical asymptote. And as we know from vertical asymptotes, there are places where a graph, I'm going to draw the vertical asymptote as a dotted line here, for some reason splits. Maybe they both go up. Maybe they split left and right, but it kind of would be nice to know what's going on there, right? No matter how we look at this, though, even if both of our branches were for some reason to split upwards, we have what's called an unbounded limit, okay? Let's hold on to that idea for a second. Let's take a look at this one, okay? The limit as x approaches pi over 2. What's this guy going to be? That'd be 1 plus cosine of pi over 2 over cosine squared of pi over 2. Cosine of pi over 2, that's pi over 2 is the top of our unit circle. Cosine of pi over 2 is 0 over cosine of pi over 2. That's 0 down there, so it's 0 squared. I'm going to just say we aren't going to be reviewing evaluating trig expressions. You just got to be able to do them right away. So please go back and study that stuff if you need to, or reach out to me if you need help doing that. That gives us 1 over 0. Oh my gosh, look, we got the same kind of thing, right? We have another infinite discontinuity. We have another vertical asymptote. I guess I didn't finish saying vertical asymptote up here, did I? Asymptote. We have another vertical asymptote. Okay, so that's going to be another sort of unbounded limit as our graph approaches pi over 2, or in this case, the number 1, 3. Our graph is going to be unbounded. It's going to extend up to positive infinity, negative infinity, or maybe both, depending on which side, right? So let's take a look at this third one and see how we can relate all of these. Okay, as x approaches 1 from the right. This is going to be interesting. So that'd be cosine, as x approaches 1 from the right. So x here is getting closer to 1 from the right, 1.1, 1.001, 1.0000001. So the inside of that parentheses, as x approaches 1 from the right, it's going to approach positive pi minus 1, because x is kind of approaching 1, right? So it really just becomes cosine of pi over the natural log of 1, but from the right. Natural log of 1. A cosine of pi is negative 1 minus 1 over the natural log of 1. That's asking us, if you need to go back and study logs, please go do that, or ask me for some ways to do that. The log base e of 1, so natural log of 1, is 0, because that's asking us e to what power gives me 1. The answer is 0. And so, oh my gosh, look at this. Actually, we shouldn't put equal signs here. Oh my goodness. These are arrows, because you can't equal something that's undefined. Leads to something that's undefined again. Another vertical asymptote. So, what kind of relates all of these kinds of situations, we run into the issue of having some what we call unbounded or infinite discontinuity. So what makes these things similar? As x approaches a, that limit point, f of x is unbounded. That's our giveaway. We're trying to divide by 0, if you will. And so what we can say is the limit approaches, if we think about the way vertical asymptotes work, right? The limit approaches infinity, negative infinity, or does not exist. Because we could say they approach infinity if for some reason at our vertical asymptote, both sides of the vertical asymptote head upward. We could say that, hey, the limit at that value there approaches infinity. If they both go down, we can say the limit approaches negative infinity. Or if they split, we could say the limit does not exist because the left and the right side are not going to be equal. However, you are always welcome to say, because technically infinity and negative infinity are not numbers, you're always welcome to say that the limit in these situations does not exist. That is always going to be an acceptable thing. The one caveat I will give is that sometimes there will be multiple choice questions that will ask you if it approaches infinity or negative infinity. In which case we have to do a little bit of testing. For example, for this one up here with this whole natural log thing, right? Oh, that should have been, why did I put negative 1? I'm making all kinds of little mistakes on this first guy. So that should be negative 2 over 0 if we're kind of thinking about what that looks like. The situation here in this third one, maybe we could ask, well, what is that limit? Is it going to be positive or negative infinity, or not exist because it kind of branches off to positive and negative infinity depending on the side? Well, let's think. We have a negative number, natural log of 1, and we're approaching 1 from the right. So if we think of like natural log of 1.0001, natural log of 1 is 0, but anything above 1 is going to give us some positive value. So we end up basically with a negative number divided by really some positive, really teeny tiny numbers, what we're thinking about here. This is not really 0, it's really close to 0, but positive. So a negative number divided by some really small but positive number, because really we're looking at 1 just bigger than 1, something like this. So the denominator will actually be a really small number, but positive. So a negative number divided by a really infinitely tiny number, but positive, is going to lead us off into a really big negative number. So if we want to, we could actually claim that the limit here approaches negative infinity, because the numerator became negative, the denominator was really teeny tiny, but positive, and an infinitely small number here that's positive dividing into a negative number will give us negative infinity. If you need more help with this, please put in the form at the end of the lesson that you need help understanding that, and we'll go over it in more detail if you would like. All right, type 3 here. Let's see what happens here. Let's try evaluating. Let's plug in x equals 3. If I plug in x equals 3 up here, I will get 0 over 0. That's interesting. This is a little different. Well, in these situations, 0 over 0, that indicates to us that we have a hole. Not a vertical asymptote, but a hole. And what's nice about a hole is that holes are just momentary gaps in the function, which means that the limit will still exist. The left and the right will still approach the same hole there. And we know from our talk about limits that you actually don't need a point there. So holes are actually okay. We just got to eliminate the holes. So all we do is this. If we want to eliminate the hole and figure out the limit, we need to figure out what's causing that hole. So let's factor the numerator here. X minus 3, x plus 3 over x minus 3. Look at that. There's where our hole is coming from. It's the x minus 3. That's the issue. So let's divide those away. This is going to be equal to whatever the limit as x approaches 3 of x plus 3 is. That's easy. 3 plus 3 gives us 6, and there's our limit. We eliminated the hole by factoring and found the limit. It's a useful tool. Let's take a look at this one. If I plug in 3, I get 0 in the numerator again. Oh, we shouldn't put equal signs, Markwalter. There we go. 3 squared minus 18 plus 9. Ooh, that's also going to give us 0 in the denominator. We got another hole. So let's take a look and let's see what we can factor. So the numerator factors into x minus 3, x plus 3 over x minus 3. What else? X minus 3, and then, oh, look at that. It's x minus 3 and x minus 3. All right. Let's see what's going on here, right? So those x minus 3's will cancel out. And what will that leave us with? That'll leave us with the limit. Notice I'm keeping my limit signs all the way through. You have to do that. The limit as x approaches 3. Oh, I double wrote my limit. That's weird, though. Don't do that. You just have to keep your limit notation, but you don't have to go overkill there. All right. What's left in the numerator? It's x plus 3. What's left in the denominator? X minus 3. Oh, look at this. I plug in 3. I get 6 over 0. I end up like above. This is going to be a vertical asymptote. We have an infinite discontinuity. So I'm simply going to say here then that the limit as x approaches 3 of x squared minus 9 over x squared minus 6x plus 9 does not exist. And again, like I said above, we're okay with that. If we have a vertical asymptote, that's going to be something infinite. I'm okay just saying, unless it's a multiple choice problem, that the limit just does not exist because it's going to give us some unbounded limit. Let's take a look at this guy. So if we evaluate here, and we plug in 4, I get square root of 4 is 2, minus 2 is 0, over 4 minus 4. Oh, that's interesting. That gives us 0 also. We have a square root here, so we can't do the same kind of factoring thing. There's a way to, but I like to think of it this way instead. If we're dealing with situations where we have like radicals like this, we can multiply by what's called the conjugate. If we see that radical, we can multiply by the conjugate. So what we can do in this case is maybe something like this. The limit as x approaches 4. I want to keep my original expression there, but the conjugate of a radical expression is exactly what you see, but with a plus sign between it. And the job of the conjugate is actually sort of undo our difference of squares rule. I'm going to multiply by the conjugate on the numerator and the denominator because I got to keep the same value. I can't just multiply the numerator. And I can rewrite this limit like this. Okay, think about the way this works. Square root of x times square root of x will give me x. Square root of x times plus 2 and square root of x times negative 2 will cancel out. And then negative 2 times negative 2 will give me negative 4. That's the really nice thing about the multiplying by the conjugate. You basically get rid of the square root, keep the minus sign, and square the back part. If you need to look up multiplying by conjugate, you can see how that works or ask me for more help. All right. In the denominator here, we can maybe keep something like this. We don't actually necessarily need to multiply out everything. We can simply keep x minus 4. And I like keeping that because notice, look at that. I have an x minus 4 up top. That will cancel too. times the quantity. If we were to put it in parentheses, because it's its own quantity, we multiplied square root of x plus 2. Oh, look at this. Now our troublesome spot will divide away, and we get the limit as x approaches 4 of 1. Don't forget the 1 up top. We still have a 1 up there over square root of x plus 2. Square root of 4 is 2, so that's 2 plus 2, which will give us 1/4, and there is our limit. Nice. So that's multiplying by the conjugate. Conjugate. It comes from the Latin word to join, together. It actually gives us things about marriage and stuff in Latin too. All right. Here we go. Let's keep moving ahead. Lots of examples today, I know. All right. We got a trig thing going on here. If I plug in, quote unquote, 0, I would end up with the limit as x approaches 0 of sine of 0. But wait a minute. The sine of 0 is 0, right? And what's the tangent of 0? Well, tangent is sine over cosine, right? Tangent of x is sine of x over cosine of x. So if I substitute in 0, I get sine of 0 over cosine of 0. That's also going to give me 0. Tangent of 0 is 0. So I got something to take care of. But I can use this little identity over here to help me out. If I want to simplify this, the limit as x approaches 4 of sine of x over tangent of x, I can rewrite tangent of x as sine of x over cosine of x, right? And that's actually really nice. Dividing by a fraction is the same thing as multiplying by its reciprocal. So this will be the sine of x times cosine of x over sine of x, multiplying by the reciprocal there. Then we notice the problem spot will divide away, leaving us with simply the sine. Oh, I'm not sure why I put a 4 there. That's interesting. That should be a 0. That guy should be a 0 as well. The limit as x approaches 0 of the thing that's left over here is cosine of x, which is going to be, hey, what's the cosine of x? I can just substitute that, and that's not the problem. It is 1, and there's my limit. And one last limit to think about. This one is an interesting one. If I substitute in 0 over 0, you can really easily tell, 0, I mean, we can really easily tell we get 0 over 0. But this guy has an absolute value. It's a little different. We can't just like cancel things out. That kind of sucks. So what do? This is actually a kind of a special case scenario that you need to remember. This is a limit I just want you to memorize, okay? Let's think about what the graph would be. If I pick any number less than 0, -2, -3, -4, -pi, -1.72, I would get a positive version of that number up top and a negative version of that number below. A positive number divided by its negative self will give us a value of -1. Try it. Plug in any negative number and you'll see that. So our graph actually hovers here at -1, but when x equals 0, it's undefined. And then if I plug in any positive number, 2, 3, 4, 5, 7.5, I get a number positive divided by itself. That's going to give me a value of +1. So we actually have these kind of two branches. They're flat at -1 and then flat at +1. That means when x approaches 0, the left and the right branches are not coming together, and so our limit does not exist. For this one, I want you to just simply memorize, if you see this limit expression, the absolute value of x over x as x approaches 0, or flip this, x over absolute value of x, limit simply does not exist. Don't be fooled by that one. Okay. What makes these similar? When we get 0 over 0 or infinity over infinity, we call these indeterminate forms. We'll see that word come up several times this year. Indeterminate forms like this are what's key here. And we have to change the form of the expression, usually by multiplying by a conjugate or factoring or being a little clever there. So you can go ahead and put a note, factoring, etc. etc., I should say. All right. Pause for a second and take a breath. Y'all are doing great. I know this is still really introduction of stuff, seeing a lot of examples. All right, here's what I'd like you to do. I want you to take a look at these next two problems. Pause the video, give them a shot, and then come back and check your work against mine. All right, let's take a look. We're trying to find the limit as x approaches -4 of this function here. Let's just go ahead and plug in and see what we get. The limit as x approaches -4. And please, please, please always keep your limit notation. I'm not going to be there all the time to check that you're doing it like I would in class, but it is incorrect. There are no questions. There's no waffling on this. It is incorrect if you do not write proper limit notation until you've evaluated that limit. All right? So there we go. If we substitute in, we maybe just do this in our head, actually. Maybe that'll help. If I plug in -4 up top, I get -6, right? If I plug in -4 down here, I get 16. Oh, man, we get something in there, don't we? We get 16 minus 8 minus 8. We have an issue, right? What we end up with is this does lead us to -6 over 0. So like I said, this is a vertical asymptote. It's an unbounded situation. We can say the limit does not exist, D and E, because the limit, I lost my article there, the article the, because the limit as x approaches -4 of x minus 2 over x squared plus 2x minus 8 is unbounded. All right. Let's take a look at 16 here, example 16. All right, this was interesting. We're trying to find the limit as x approaches -2 from the right. This one, each year, some people have some trouble with. This one, since we're asking for the limit from the right, let's dig into this a little more. All right. You might simply plug in your head and say, oh, that's -2, -2, over -2 plus 2, that'll be 0 squared. So it's going to be unbounded. It will be. So technically the limit does not exist here. So if you want to, we can say that the limit as x approaches -2 from the right of x over x, well, that's starting to blend together. I don't like that. X over x plus 2 squared does not exist. True. But I want to dig into this a little more. What if we wanted to know whether or not this unbounded limit from the right is going to be positive or negative? All right. Well, let's try this. We could say then that the limit as x approaches -2 from the right. So approaching -2 from the right, that means the numerator, right? The numerator is going to be close to -2, right? Essentially, our numerator is going to be -2. I should back up and do this. Limit as x approaches -2 from the right of x over x plus 2 squared. The numerator is really going to approach -2. Right? I'm going to use the arrow because this isn't really going to be equal. -2 over. Now let's see what happens in the denominator here. The x value here is going to approach -2 from the right-hand side of -2. So that's going to be like -1.9999999999999 plus 2. That's going to take me positive. Then we're going to square it, so that's still going to be positive. It's going to be a really teeny tiny number, but positive. So if it helps, you can put tiny positive. Right? You can do that, or you can put 0 plus. It's going to be a positive number, really tiny. Some number divided by an infinitely tiny positive number, so a negative number divided by an infinitely tiny positive number, is going to lead us to the fact that this limit, if we want to think about it this way, actually approaches -infinity. What that means at that vertical asymptote from the right-hand side is that our graph actually shoots down at that vertical asymptote. All right, plowing ahead. Let's see, given this, this piecewise function here, let's determine the limit as x approaches 3, or explain why it does not exist. Now here's the issue. With piecewise functions, we have breaks here, right? Our graph is going to be chopped up into little intervals. So if the limit is going to exist here, we need to know that the left-hand limit and the right-hand limit are going to approach each other. So let's check the limit as x approaches 3 from the right of g of x. Well, from the left of g of x. From the left, that's this top branch right here. So if I substitute in 3 into my top branch, that's to the left-hand side of 3. I get 2 minus 3, which will give me negative 1. So let's check the right-hand side, the limit as x approaches 3 from the right-hand side of g of x. The right-hand branch is this one right here, the middle one. We plug in 3 into the right-hand branch. That's 3 times 3, which will give me 9. So we can say the limit as x approaches 3 of g of x does not exist because, look, our left-hand and our right-hand limits are not equal. So I can simply say the limit as x approaches 3 from the left of, not f of x, of g of x does not equal the limit as x approaches 3 from the right of g of x. So therefore, our overall limit does not exist because the left-hand branch, the top branch, and the right-hand branch, the bottom branch, are not going to have the same value as we approach 3 by plugging in. All right. I want you to pause the video and try the practice problems on the rest of this page. Notice at the bottom on 15 here, there's this. This is actually supposed to go with the next page, so just ignore this piecewise thing at the bottom. I want you to try 1, 2, 3, 4, 5, 6, and that graph just underneath it. Go ahead and pause the video and give that a shot. All right. Quick go through here. We always start, if we can, by just plugging in. So we're going to plug in. That'll be 9. This is going to give us 9 times 2 minus 3 is negative 1. So that's going to give us a limit of negative 9. Let's try over here. If I plug in 2, I get 4 plus 4 plus 4 over 2 plus 2 is 4. So that's going to give me 12 divided by 4, which is 3, right? Let's take a look at this guy. Ooh, let's see. Something's a little different here. I can already tell because I know the denominator is going to be 0. So this is going to lead us to, if I plug in 1, that'll be 2 plus 1 minus 3. 2 plus 1 minus 3 over 0. That's going to give us 0 over 0, huh? So we got to do some factoring here and figure some stuff out. What's nice about this is we do have some clues here about the factoring. We know that there's going to be a hole, and that's got to cancel out with x minus 1. So I can simply use that to help me with my factoring. So I know one of the factors up here is going to be x minus 1, which means the other factor has to be 2, and then probably x plus 3, right? Because I need a 2x up front. I need a minus 3 when I FOIL back here. We can do a quick check. X times 2x will give me 2x squared. X times 3 will give me 3x. Minus 2x will give me just 1x. And a minus 3 at the very end. Great. Over x minus 1, my whole will cancel out. And I'm left with the limit as x approaches 1 of 2x plus 3, which is going to be 5. There we go. All right, let's take a look at this one. Oop, I can already tell we get 0 over 0. So let me go ahead and do some factoring in here, right? This is going to be the limit as x approaches 0 of x over x times x minus 2. I'm going to factor out the x from the denominator. We'll lose those guys. And we get the limit as x approaches 0 of 1 over x minus 2. I plug back in 0, and I get 1 over negative 2. All right. I love this one because it actually teases something we're going to be doing later. If we plug in 0, wait a minute, we get 0 over 0, don't we? I can tell we get 4 minus 4 over 0. So we got to have some way to deal with this. This doesn't look like it factors very well, but actually, if we take the time to expand what we're looking at there, if we take the time to expand this squared term here, here's what we get, right? We get 4 plus, then I would have 4h plus h squared. That's that expanded there. If you need to, take the time to FOIL it out. Minus 4 over h. Now look what happens. We lose that 4. We lose that 4. And we get the limit as x approaches 0. We started out as 0 over 0, so I got to have some things that will cancel out here. I'm seeing some things clean up. That'll give me 4h plus h squared over h. Wait a minute. I'm starting to see what's going on here. Ooh, this should be an h approaches 0, not an x. The limit as h approaches 0. I can factor an h out of the numerator. That'll be 4 plus h over h. We'll lose an h, and that'll give me the limit as h approaches 0 of 4 plus h, which will give me a value of 4. All right. So we do know in here that this limit will be unbounded. If I plug in -3, I get -3 over 0, but we're approaching it from the left, so let's figure out if this approach is positive or negative infinity. So the numerator here, I'm going to use my little arrows, not equal signs, because we're just kind of thought processing. My numerator is going to be approaching -3, but in the denominator, -3 from the left, so that's -3.00001. It's something smaller than -3. So something smaller than -3 plus 3 is actually going to leave me with a really tiny but negative number, right? -3 from the left means -3.0000001, and then add 3 to it. I'm still going to be negative, teeny tiny but negative. So a negative divided by negative is going to lead us to an infinite, positively infinite result. Okay. Take a look at the graph here. We want the limit from the left, which will be 1. We've run it in from the left-hand side. The limit from the right is going to approach +2. Remember, we care where it's pointing toward here, +2. The limit overall then does not exist because the left and right-hand limits are not the same. But f of 1, where is that point? It's at 2. All right. Cool. Pretty good. We're getting pretty close to the end here. Let's do this. To wrap up with here for today, what I would like you to do is take a look at this piecewise function that's at the bottom of 15. At the bottom of 15. And I want you to evaluate, use that piecewise function to evaluate 9a through I, and answer these 2 graph questions as well. And we'll stop. I'll pause the video, and then you'll try those, and then you'll check your answers, and we'll wrap up. All right. So again, we're going to use this piecewise function at the bottom of 15 to answer 9a through I, okay? So let's take a look as x approaches -1 from the right. So we got to be careful here. We got this branch here, -1 from the right-hand side is this first one. So that's up here, the right-hand side of -1. So -1 plus 2 will give me a limit of +1. X approaches 0. Well, 0 is in this interval. So I actually have no issues. I can just plug in 0. 0 plus 2 is 2. -1 from the left. So -1 from the left is going to be this branch over here, the branch that's less than -1. So I'm going to plug in -1. -1 squared plus 1 is going to give me 2. Cool. Those are the first 3. Let's take a look then at zoom out actually a little bit. Maybe that'll help. Cool. Let's take a look at D then. Take a look at D. D is asking what happens as x approaches -2. Well, where is the next value of -2? -2 is in this branch up top here. It's solidly in that branch. So -2 squared is 4 plus 1 gives us 5. How about -1? As x approaches -1, this approaches -1 overall, right? Overall. So we need to check the left and the right-hand limits, which we actually already did. We found that the left-hand limit, the right-hand limit from the second branch was 1. And we found that the left-hand limit as x approaches -1, the top branch there, was 2. So since the left and the right-hand branches don't line up, the overall limit does not exist. All right, x approaches 2. X approaches 2. I have to deal with both the left and the right-hand branch. So let's check those. The left-hand branch of 2, as x approaches 2 from the left, is 2 plus 2, which is 4. Actually, that's the answer to I, so there we go. And how about the right-hand branch, the bigger than 2 branch? As x approaches 2 from the right-hand side, the bigger side, 2 times 2, that will give us 4. Oh, so the limits from the left and the right are equal, so the overall limit does exist, and it is 4. And lastly, the limit as x approaches 4 overall. Hey, 4 is bigger than 2, so I just plug in here, and that'll give me 8. All right. Cool. Let's take a look at those graphs and wrap up. All right. Cool. So here we got a graph. We want to know what happens as x approaches 2 from the left. Looks like we got a vertical asymptote from the left. our limit approaches positive infinity. If we can, we want to be specific. Don't just say it does not exist if we can help it. From the right-hand side, looks like our limit from the right-hand side approaches negative infinity. Oh, the left and the right-hand side are not the same, so the limit does not exist. What about f of 2? There is no point at f of 2. It's a vertical asymptote, so f of 2 also does not exist. All right. And another graph here. As x approaches 2 from the left, looks like we approach positive infinity. We shoot up there. As x approaches 2 from the right, it also approaches positive infinity. So if we want to, we actually say the overall limit approaches positive infinity. Like I said, technically we could also say it does not exist, but if we can be specific, I like that. How about f of negative 2? Well, there is no point there. It's a vertical asymptote, so the point f of negative 2 does not exist. All right. Cool. So I have included in this packet, there are some other practice problems that you're welcome to try if you're looking for more help. We will have time to practice with different limits and things along the way over the next couple days. I do want to draw your attention to one last thing and then talk about the optional homework. There are 3 sort of special case limits. We already talked about this one that you should just memorize. The limit as x approaches 0 of absolute value of x over x does not exist. The limit as x approaches 0 of sine of x over x is 1. If you go and graph this function, you will see that, all right? The graph at x equals 0 does approach 1, even though it does have a hole there, all right? And then sort of one other interesting limit, once it involved the sine of x, sine of 1 over x, so we could even simplify this, the limit as x approaches 0 of sine of 1 over x does not exist. You can think about why. If we have 1 divided by some really teeny tiny number, not 0, but divided by, remember, it's approaching 0, so 1 divided by infinitely tiny number makes the inside of the sign here, the argument, huge, infinite. 1 divided by teeny tiny number close to 0 gives an infinite answer for this fraction. But think about the way a sine function works. A sine function just keeps doing this out to infinity. It keeps going up and down, which means we want the sine of something bouncing back and forth. It never approaches a number, it just keeps bouncing back and forth as we go off to infinity. So the limit here does not exist. Okay, so there's something to memorize there. But then what happens if we multiply by x cubed as x goes to 0? Well, sine is finite, right? The sine function is stuck between a maximum of 1 and a minimum of negative 1. And then if we multiply it by x cubed, but x is going to 0, and multiply that by 0, this limit becomes 0. We take sine, which is finite, between positive 1 and negative 1. Those are the maximum and minimum. And then multiply it by 0. It is going to kill it and make it go to 0. So these are 4 things I do want you to have memorized in terms of limits that are kind of special limits, okay? What I'd like you to do now at this point is when you're done with this, there will be a little exit ticket to take just to test your knowledge for a second. There are also optional homeworks, both for the live 1.1 class and this asynchronous lesson. They are optional. I highly encourage you to do them because it's what I would typically assign during a normal year in class, and they are what makes people be ready for the test and the exam at the end of the year. I highly encourage you, if you really want to know calculus, please, please, please do the optional homework. Veterans, I've taken this out for this year. We're not going to be doing this. So it is just the optional homework that's listed there, and you'll see on the Nearpod. Please take the exit ticket, fill out the survey at the very end of the Nearpod, and please try the optional homework assignment. Take care, everyone.